Hi everyone, welcome to another of my videos on computer systems. This will be the fifth video in Module 1. We're talking about representing numbers. And now that in Part 4 we went over the basics of floating point, we'll get a little more deeply into it and talk about some specific operations and how exactly we go about converting a simple numerical value, a simple real number, into a floating point representation. Now, let's first talk about just what is the basic idea when we do floating point operations. Well, if we're going to take two floating point values, x and y, and add them together, what we're actually going to do is add x and y, and then we're going to round the result to whatever precision we can kind of fit into our floating point representation. Same thing will happen with multiplication. So again, the basic idea is we compute the exact result, and then we make it fit into the desired precision. But there's a couple things we have to keep in mind. If the exponent's too large, we might overflow. All right, remember, we only have a certain number of bits to express our exponent, and we have to take the bias into account as well. So for single precision floating points, we've only got 8 bits for the exponent. So we've got to make sure that we don't have a value that's going to overflow that. And we might have to round to fit our significand into our frac field, right? Or at least our representation of our significand. Because again, we only have a certain number of bits for that. So that's where our rounding comes in. We might not be able to get an exact result. Now, since we've been talking about rounding, let's talk about a few different options that we have. These are called rounding modes, and we'll just illustrate this with currency because hopefully that'll be pretty easy to follow. So if we're rounding things to the nearest whole dollar value, there's a few different ways we can do this. And these are going to be the values that are nearest according to the mode that we're using. So the first one here is toward 0. We'll just always go toward 0. So $1.40 will be 1, $1.60 will be 1. Anything, $1 anything will just go to 1. $2 in anything, so like $2.50 would go down to 2. And negative $1.50 would go, again, that would go toward 0, so that's going to round to negative $1. So that's something to be a little careful of. We don't just knock off the whatever's, past the decimal point. We go toward 0 for each operation. So sure, $1.60 is actually closer to $2, but if we're rounding toward 0, then the closest whole dollar that we get using that mode is going to be $1. We can round down toward negative infinity. All right, so we'll actually always go, if there's any rounding to be done. Now, if we start out with a value of $1 or $2, then we don't actually have to do any rounding. We're already done. But if there's any rounding to be done, we always go lower. So 140, 160, 150, again, these are all going to end up being $1. 250 ends up being $2. We just knock that again down toward negative infinity. We get a different result for negative 150 because instead of going toward 0 and going up to negative $1, we're going to go down toward negative infinity and go down to negative $2. If we round up, it's just the opposite, right? 140, 160, 150 go to $2. 250 goes to $3, and then the negative 150 again goes up all the time because we're rounding up toward positive infinity. So negative 150 would go up to negative $1. And our default mode, though, what we're usually going to see when we're dealing with computer systems is nearest even. Now, all that means is we're going to do what we would expect from kind of normal rounding that we've always done. We'll go to the whole dollar amount that we're closest to. So for $1.40, we'll go down to 1 because we're closer to 1 than to 2. For $1.60, we're actually closer to 2 than to 1, so we go up to 2. But what happens with $1.50 or $2.50 or negative $1.50? Well, in that case, nearest even says if we're exactly halfway in between, right? If we can't make a decision by just being closer to a whole value, we will go to the value that makes the least significant digit of our result an even number. So the 150 I could either go down to 1 or up to 2, but I'm rounding to the nearest dollar, so my least significant digit is that dollar value in the ones place of the dollar value if we're dealing with, tens of dollars or hundreds of dollars. But what we're going to do is go to the one that makes that least significant digit even, and of course, that means we go up to 2. For 250, if we went up, we'd end up at 3. That's an odd value, so we'll go down in that case. So even though for both of those examples, $1.50 and $2.50, we're exactly halfway in between. We go in one direction with the 150 and the other direction with the 250 because we're going to try to land on an even value in our least significant digit. And then for negative 150, we'll actually go down to negative $2 because, once again, that gets us to where our least significant digit has an even value. Now, since round to even is our default rounding mode, let's dive a little deeper into why that is and exactly how it works with some more examples. It is our default rounding mode for a couple different reasons. First of all, it's hard to get any other kind without dropping into assembly, and we'll be looking at assembly in future videos within this series, so don't worry too much about the exact nature of why that is. We'll see that in further videos. But another thing that makes it handy that this actually works a little easier as far as implementation goes is that the other methods of rounding tend to be statistically biased. So our set of positive numbers would consistently be over or underestimated by using any of those other rounding methods. So this works out nicely for a couple reasons. One, it's a little easier to implement in high-level languages, and it takes care of that statistical bias. So let's take a look at some more examples on this because we really want to make sure we understand this moving forward since this is how we're going to be doing things. So let's take a look at other decimal places or bit positions, because in those last examples from the last slide, we were talking about rounding to whole dollar values. We were basically talking about rounding to the ones place. What happens if we want to round to the nearest 100th? All right, so if I've got 7.8949999, etc., a bunch of nines, I'm going to round down to 789 because I'm less than halfway, right? That's our first rule for round to even. If you're less than halfway, you round down. If you're more than halfway, you round up. We always round to the nearest value that we're looking for, that has the precision we're looking for, unless we're exactly halfway in between, and then we have a design decision to make. So if I'm at 7.895, a bunch of zeros with a 1 somewhere, if I got some weight further on down, I'm greater than halfway up to 7.90, so I just round to 7.90. But these last couple, if I've got 7.895 and then a bunch of zeros, I'm exactly halfway between 7.89 and 7.90. Well, if I rounded down, I would end up with a 9 in my least significant digit. Uh-oh, that's odd. So I better go up. So when I round up to 7.90, I end up with an even number in my least significant digit. That's round to even. Same kind of idea with 7.885 and then a bunch of zeros. If I were to round up to 7.89, I land with an odd number in my least significant digit, so that's not going to work. So in that case, I round down to 7.88 so that least significant digit ends up being even. Now, the good news is that this works exactly the same for binary numbers. When we're dealing with binary fractional numbers, we consider it even when the least significant bit is 0, and halfway when the bits to the right of the rounding position take the form of a 1 followed by a bunch of zeros. So we just take a look at the bit to the right of our rounding place and all of the other bits following that. If it takes the form of 1 followed by a bunch of zeros, it's exactly halfway. If it's a 1 and then there's some weight after that initial 1, then it's more than halfway. If it's a 0 in that position to the right of the rounding position, then it's less than halfway. So this is actually pretty easy and intuitive to figure out as well. So let's look at examples of this. Let's say we're going to round to the nearest 1/4. Now, remember that we're talking in binary here, so the bit to the right of the binary point has a weight of 1/2. to the right of that has 1 over 4, etc. So if we take a look at our first example here, if we've got 10.00011, and we want to round that to the nearest 1 over 4, so again, that's 2 bits to the right of the binary point, then the bits that we want to focus on when we figure out how we're going to round is this 0, 1, 1 that you see in red here. Now, that's a 0 followed by some stuff, and we know that when the bits to the right of the rounding position start with a 0, it's less than halfway, right? So we're just going to round that down. We round that down, and rounding down, we just knock off all that extra stuff, and we're left with 10.00. So that one's pretty easy. Another one that's pretty easy, actually, is if we look at this 10.00110. The bits we're focusing on are the 110 in red here. And, well, we just look at it and compare it to our bit pattern, right? We have a 1, and we don't just have a bunch of zeros following that first one. We've got some weight there, so that means it's greater than halfway. So we'll round it up to 10.01. So far, so good. Very intuitive, pretty easy. Now we get to the interesting stuff where we have to apply this round to even. So we take a look at 10.11100. The bits we're interested in are the 100. Those are the bits to the right of our rounding position. And that does match our pattern, right? It's just a 1 followed by zeros. That means it's halfway. Now, if we round it down, we'd end up with 10.11. Uh-oh. 1 in that least significant bit is odd, so we don't want to do that, so we'll end up rounding up, and when we do that, we add 1, and so when we do the additions and carry things over, we end up with 11.00. We've rounded up to take care of our round to even. This last example, 10.10100, bits in question are the 100. That matches our pattern, so we know that we're exactly halfway between the two values. If we rounded up, oh, we'd have to add 1. We'd end up with 10.11. Again, that's an odd number, so we can't do that. So we'll go ahead and in this case, we'll round down and get 10.10. So all of this, it's a little bit different when we're dealing with binary. We just have to keep that in mind, you know, how many different values we have to work with in each bit, as opposed to having 10 for each digit in a decimal system. We only have 2 for each bit in a binary system. But keep in mind, these work under the same rules. If you understand it for decimal, then you understand it for binary. So don't let the binary be intimidating for you. It works exactly the same. Now that we've covered all of that, this is what we do when we talk about fixing something when we've done a floating point operation. So in floating point multiplication, all right, we're going to just multiply 2 floating point values together. The exact result will be -1 to the s times m times 2 to the e, right? Just our normal floating point description. The sign will end up being the sign of the first value exclusive ORed with the sign of the second, and that makes a ton of sense, right? I mean, that makes all the sense in the world, because when we think about it, when we multiply 2 negative numbers together, we get a positive. When we multiply 2 positive numbers together, we get a positive. We multiply a positive and a negative, we get a negative. That's exactly how exclusive OR works, right? Because remember, that sign bit, a 1 indicates a negative value. So if it's 1 and 1, so a negative times a negative, we get a 0 or a positive, and so on through the truth table. The significand is just the significand of the first multiplied by the significand of the second. That's easy enough. And with the exponents, we just add them. And we've done this before, right? This is basic algebra stuff. This is just how exponents work. 2 to some exponent times 2 to some exponent is 2 to the 2 exponents added together. So the fixing is where we get into our rounding, where we get into things where we have to shuffle things around a little bit. So if m is greater than or equal to 2, right, we have to shift m to the right and then increment e to take care of the fact that we've shifted m to the right. We've effectively moved the binary point to the left, so we have to increment e to reflect that. And the reason that we care about whether m is greater than or equal to 2 is because with floating point, we either have an assumed leading 0 or an assumed leading 1. There's no such thing as an assumed leading 1, 1 or more. when we're dealing with our floating point representation. So if m is greater than or equal to 2, that means we have a 1, 0 at minimum to the left of the binary point. That doesn't work, right? If it was greater than 2 or equal to 2, then we've got a couple of bits that are to the left of our frac field, and that doesn't fly because we're not directly representing those. We have an implied 1 for normalized values or an implied 0 for denormalized values, so we have to make our representation fit those assumptions. Now, once we've done that, again, we have to increment e if we've shifted m. Now, if e goes out of range, we have an overflow. And once we've taken care of that stuff, right, we've gotten our significand into a form that will work for representing in floating point. We've modified our e and made sure that we can actually still represent that e within the bits that we have in our exp field. Once that's taken care of, we just have to round our significand so that we can fit it into the bits we have available in the frac field. Now, the biggest chore of this, it might sound a little complicated, but we're actually going to do some examples of this a little further on in the video, and it's not scary at all, I promise. The biggest chore is just multiplying the significands, actually, right? Remember when we talked about multiplying integers, that can be costly. That's the biggest, hardest thing we actually have to do, is multiply those two values together. For addition, it's really not all that different. We're still sort of messing around with the values just to make everything line up and fit into our representation. So when we add two floating point numbers, the biggest trick is to get the binary points lined up just like we would when adding in decimal, right? We generally don't want to put, 10.1 and then add to that, 100.01000. And when we write that down to just do it by hand, we're going to line up the decimal points. Well, we do the same thing with binary and floating point representations. So our exact result is just going to be, again, our normal floating point representation. The sign and significand are just the result of a signed, a line, and then add. So we just need to shuffle things around so that the exponents are the same, basically, right? We just have to shuffle things around so that we've got our binary points lined up. And then we're going to just go ahead and do a bit by bit. We'll just add it up. To start with the least significant bit and carry if we need to, but we just do a normal addition just like every addition we've done since grade school. And the exponent will end up being equal to E1, assuming E1 is greater than E2, that's the value of E for our result is going to be the greater of the exponents because we're going to align to that. And then we just do our fixing. Right, just like we did with multiplication. If m is greater than or equal to 2, we shift m to the right and increment e. If m is less than 1, we shift m to the left k positions, however many we need to get that implied leading 1 or 0, and then we'll decrement e by the number of places that we've shifted it. So if we shift m to the right, we increment e. If we shift m to the left, we decrement e. We overflow if e is out of range on either side. And then we round m to fit into the bits that we have available in our frac field. So again, it's basically the same idea. The addition and multiplication are very straightforward. There's nothing that we haven't looked at before that's going on in finding that exact result. It's the fixing that gets interesting with floating point because that's where we might have to shuffle things around to make sure that it corresponds with our floating point representation. And those rules, like those implied leading 1s and 0s and the values that we have available to represent in our EXP field. So let's talk about mathematical properties really quick because once again, floating points aren't the same thing as reals, right? We mentioned that previously, actually, in sort of the introductory video. We talked about how integers are not just natural numbers and floating points are not just real numbers, that because we have these finite representations, things might not work when we're dealing with a computer system in the same way that they would when we're just dealing with abstract mathematics. And it's important for us to know what the differences could be and when we might run into trouble because of them. So let's look at floating point addition, and we can compare to the kinds of properties that we talk about when we're dealing with an abelian group. Now remember, an abelian group is basically just a group of things that you can apply commutativity to. So let's go through these one by one, and we'll talk about what we mean. So first of all, is floating point addition closed under our floating point numbers closed under addition? Yes, they are. All right, and remember that means we're talking kind of about set theory, where we say if we apply an operation to two elements of the set, we're guaranteed to get another element of the set, out of the other end of the operation. And that's true for floating point numbers, but we want to keep in mind they might generate an infinity or a not a number. It's still something we can represent with floating point representations, so it's closed under addition, but it might end up giving us one of those special values. Is it commutative? Basically just, does A plus B the same as B plus A? Yes, it is. We're not going to run into any surprises there. Is it associative? Oh, there we run into an issue. It's not associative, right? So adding natural numbers would be, but with floating point, it's not. And that's due to overflows and the inexactness of the rounding that we have to do when we're fixing our results, right? When we're shuffling things around and rounding things and making it fit into our floating point representation, that can mess us up as far as associativity goes. And here's an example of that. If we take 3.14 and add 1 times 10 to the 10th to that, and then we take that result and subtract 1 times 10 to the 10th, we're actually going to get 0. You would kind of expect it to be 3.14, but it's not because of overflows and rounding, right? That 1 times 10 to the 10th in the first set of parentheses there overwhelms that 3.14, and the whole thing just gets rounded right out. Now, if we switch around the order in which we do these things, and we take 3.14 plus the quantity, 1 times 10 to the 10th minus 1 times 10 to the 10th, well, those 1 times 10 to the 10th minus 1 times 10 to the 10th just evaluates down to 0. We add 3.14 to 0, we get out 3.14. So it's not associative. The order in which we do the operations matters as far as the result that we're going to get. Is 0 an additive identity, right? Is anything plus 0, you just get the anything back out? Yes, that's true. Now, does every element have an additive inverse? Almost. Because infinities and not a numbers don't, right? So if we're in the normalized or denormalized range, we're fine. Yes, we're going to have an additive inverse for each element, but when we get into infinities and not a numbers, that's where we don't. So it's close, but we want to, again, keep those special cases in mind, and that's the same thing when we deal with monotonicity, right? Now what that's talking about is if A is greater than or equal to B, does that imply that A plus C is greater than or equal to B plus C? So if I take an inequality, add the same number to both sides, is that relationship going to hold? Again, almost. That's not really the case for infinities and not a numbers. So for these last couple, the almosts, okay, it's pretty close, and if we're in a normalized or denormalized values, when we're talking about how 0 acts, all of that is fine. It's just as you would expect it to behave mathematically, but it's an almost because of those special cases of the infinities and the not a numbers, and we always want to keep in mind that associativity will break down when we're dealing with floating point addition. And we can do the same kind of thing looking at properties of floating point multiplication. In this case, we compare it to a commutative ring. Is it closed under multiplication? Yes, but may generate infinities or not a numbers. Is it multiplication commutative? Yes. Associative? No, for the same reasons, right? We have different examples here, but it's the same idea. We might overflow, we might add some inexactness because of rounding, and so associativity breaks down under multiplication as well. 1 is the multiplicative identity, just like 0 is the additive identity. Does multiplication distribute over addition? No, it does not. So when we take a look at these examples where we have something multiplied by a quantity, right, we would normally think, just applying abstract mathematics, that we could distribute that value into what's in the parentheses and just multiply it by each individual thing and then finish up the operations within the parentheses. That does not work with floating point either, for the same reason that associativity doesn't work. Because of overflow, because of rounding, the order in which we do things matters, and we can get different results. So we want to keep those things in mind. Monotonicity, it's another almost, right? So in this case, we multiply both sides of an inequality by something. We would expect that to hold, and as with addition, in normalized and denormalized ranges, it does, but we have infinities and not a number. So those are the things that mess some of the stuff up for us, right? Those infinities and not a numbers don't quite work the same way as stuff in the normalized and denormalized ranges. So we want to be very careful about that. And because of overflow and rounding, the order in which we do things and how much bigger one number is than another number when we're dealing with these operations, it matters. When we can actually end up just sort of making smaller values disappear into much larger values when we add that rounding. Those can just kind of go away. So we have to be careful to keep that in mind, and to also keep in mind that the order in which we do things might change the answers that we get. Moving right along into what C does for us when we're dealing with floating points. When I sit down to write some code in C, what can I expect? How can I expect floating points to work? Well, C guarantees 2 levels of precision. When we're dealing with floating points, we've got the float type, which is a single precision float, and the double type, which gives us a double precision floating type value. Some interesting things to keep in mind has to do with how we do conversions and casting, right? So if I want to go from int to float to double and whatever combination of which of those I want to go to the other one on, we're going to change the bit representation. So this is not like going from an unsigned to a 2's complement integer was, right? Where we kept the bit representation and just reinterpreted. When we're dealing with floats and doubles, we have to keep in mind that we're going to change the bit representation. Now, if we go from a double or a float to an int, we're going to truncate the fractional part. It's a lot like rounding towards 0. It's not defined when you're out of range or not a number. So when we hit one of these undefined values, we're going to go ahead and usually set to t-min. So we're going to set it to the lowest possible 2's complement integer that our system supports. When we go from int to double, it's going to be an exact conversion as long as the int has less than or equal to a 53-bit word size. So if we get up into some kind of integer representation that has a big old 64-bit word size, that can get a little iffy. But as long as we're less than 53, and usually we're talking around the realm of 32-bit, we can do an exact conversion. So the value of the double will end up being the same as the value of the integer that we're casting from. Now, when we go from an int to a float, we're going to round according to the rounding mode that we have implemented in the system or in the compiler. We've talked about some abstract concepts, and we talked about some specifics about how floating point numbers are represented and how they're operated on. But let's take a moment at the end of this video here to go over some concrete examples of what creating a floating point number actually looks like. Let's go right through the steps, and those are going to be, we're going to normalize, and that just means we're going to set it up so that whatever we're representing, we're going to shuffle things around so that it has a leading 1. Because remember, when we're dealing with a normalized floating point value, we have that implied leading 1 when we take the frac field and we're going to turn that into the significand. We have to assume that there's going to be this implied leading 1 that we don't have to waste a bit representing. So that's our first step. We set things up so that it has a leading 1. We round it to fit within the frac field, and then we post-normalize to deal with the effects of rounding. And we'll actually see an example of what that means in these examples that we're going to go over. Now, we're going to be using this 8-bit floating point representation where we have 1 sign bit, 4 bits for the EXP field, and 3 bits for the frac field. That's going to be sufficient to represent things, and it's going to keep it a little simpler so that we're not dealing with these big, huge representations where we have just sort of a whole bunch of wasted bits while we're looking at these and just trying to wrap our heads around exactly how it works. So we'll convert these 8-bit unsigned numbers to this tiny floating point format. And here are the example numbers. We just have the numbers that we'll be converting: 128, 15, 33, 35, 138, and 63. And over to the right are the binary representations. These are just the 8-bit binary representations of these decimal numbers. So that's where we'll start. And for each of these, we'll just go through these steps step by step and see how this all works. We'll normalize them to have a leading 1. We'll round them to fit within a fraction. We'll post-normalize to deal with any effects of rounding. Step 1, we normalize. That just means that we're going to set the binary point so that the numbers have the form 1 point whatever else is left. So when we adjust all of these to have a leading 1, we have to decrement the exponent as we shift left. So since we're dealing with 8-bit binary representations, we can sort of, let's assume that the exponent would baseline at 8. Let's pretend that the binary point is to the left of the most significant bit of each of these raw binary representations. So every time we shift left, we decrement the exponent. So for the first value, 128, we would have an implied binary point followed by 1 and a bunch of zeros. We only need to move that over to the left 1 time. All right? We only have to shift left 1 time to get 1 point, a bunch of zeros. So we decrement that starting value of 8 for the exponent by 1, and we land at 7. For the representation of 15, we would have 0.00001101. We shift that over 1, 2, 3, 4, 5 times, right, to get that 1 in the spot to the left of the binary point. So we end up with 1.101 and a bunch of zeros. We've shifted left 5 times, so the exponent becomes 3. And you can see this follows right down the line. Right, however many times we have to shift to put a 1 to the left of our implied binary point that starts out to the left of each of these, we just decrement 8 by that many, and that's the exponent that we end up with. That's our normalization. And you can see that all of them have ended up with this representation that starts with a 1 dot whatever's left and the exponent that we've gotten by doing that shifting. Now, our next step is rounding. All right, we only have so many frac bits available, so we've got to make our numbers kind of fit into what we have. Now, a nice, easy way to sort of figure out how we're going to do this is by setting something called guard bits, round bits, and sticky bits. So if we take a look, all of our representations, because we've already normalized, we started out with 8 bits. We've got a 1 to the left of the binary point, and that leaves 7 bits over to the right of the binary point. We have 3 bits available in our frac field, and remember, we don't have to explicitly represent that leading 1 because that's implied. We've saved a bit in floating point by using that implied leading 1. So I need to keep 3 bits to the right of the binary point. That's what I can fit into my frac field. So I've got a bit, I've got another bit, and then I've got something that we're going to call the guard bit. That's just the least significant bit of my result after I've done my normalization. And this works for this representation or any other. We've got a round bit, which is the first bit we're going to remove. All right, these bits that are in red here, we have to drop those. We got to get rid of them because I've only got 3 to work with, and those are taken up by these. So the first bit that's going to get removed is going to be referred to as the round bit, and then the sticky bit is just the OR of the remaining bits. So basically, if any of them or any combination of them have a 1 in there anywhere, the sticky bit is 1. If it's all just a bunch of zeros, then the sticky bit will be 0. So by doing this, we can have a very simple way to figure out what our round up conditions are. If the round bit is 1 and the sticky bit is 1, right? If we're not just looking at 1 followed by a bunch of zeros, if we have a 1 followed by some weight somewhere, then we're going to be greater than halfway to our next value. If the guard bit is 1, the round bit is 1, and the sticky bit is 0, then we have to round to even. And because we're talking about round up conditions here specifically, we're going to do that by incrementing the value. Because that guard bit tells us that we currently have an odd number in our least significant bit that we want to keep. All right, so if the round and sticky bits tell us that we need to round to even, we know we have to increment to get ourselves to an even least significant bit. If the round bit is 0, then we know that we're below halfway to the next value and we round down. So we can use these to very, very easily figure out, based on these conditions, whether we're going to increment our least significant bit or not. So let's look at a couple examples. For 128, the first one we started with. Now here's our normalized value, 1 point a bunch of zeros, which means that my guard bit is that third bit over from the binary point, right? And that's a 0. My round bit is the first one I drop. That's a 0. My sticky bit is just the OR of everything else. That's a 0. So are we going to increment? No, we're not. And our rounded value, it's the same thing. It's already rounded. We're done. When we look at 15, our guard bit in this case is 1, our round bit is 0, and our sticky bit is 0. But because the round bit is 0, we know we don't have to increment. We're just going to drop the rest of those bits in red off, and we end up with 1.101. If we do 17, we have a guard bit of 0, a round bit of 1, and a sticky bit of 0. All right, so we're not going to increment because we do have that bit pattern we're looking for to know that we're exactly halfway to the next value, but our guard bit is not set. So I can just drop this. I don't need to increment. I can just drop these bits in red and end up with an even value in my least significant bit. That's what that guard bit kind of tells us. If the guard bit is 1, that's odd. So I'm going to have to increment if I've got a round bit of 1 and a sticky bit of 0. I don't have to increment if I have a guard bit of 0, even if I have a round bit of 1 and a sticky bit of 0, because just leaving it alone and rounding down, right? So not incrementing ends up leaving me with that round to even that we're looking for. Now 19 gets a little more interesting. We've got a guard bit of 1, we've got a round bit of 1, and a sticky bit of 0. That matches that second condition, which is, again, it's a round up condition. So we are going to increment that one, and we end up with 1.010. So that's one where we actually did do a change, right? With 138, guard bit is 0, round bit is 1, sticky bit is 1. When the round bit is 1 and the sticky bit is 1, we know that we're greater than halfway to the next value, so we round up. With 63, now this is one to pay attention to for the post-normalized step. We've got a guard bit of 1, a round bit of 1, and a sticky bit of 1, so we do want to increment. That's a round up condition, but when we increment, notice we add 1. That gives us a 0, carry the 1, another 0, carry the 1, another 0, carry the 1, another 0, carry the 1. Uh-oh. When we round that, we end up with 2. We end up with 10.000. That is greater than or equal to 2. And that was, remember, when we talked about fixing a floating point value, this is where we actually have to do some extra work. We have more than our implied leading 1 to the left of the binary point now, so we've got to make some adjustments. And this is where we post-normalize. So as we just saw with 63, rounding actually caused overflow. So I have to handle that by shifting right once and incrementing the exponent. Okay, so let's focus in on 63 because with the rest of these, we didn't have anything that we have to post-normalize. We've got our normal forms, we've got our exponents are just the same as what we figured out when we were normalizing. So we're okay. All we have to do now is take these values, right? We have our significands, we have our exponents, notice the capital E, so we have to adjust for the bias. We have the bits that are going to go into the frac field. We've got our EXP with a capital E value that we can translate into the values that we have to express in our EXP field in the actual representation. So we just do those little conversions like we saw in the last video and go ahead and just slap them into the representation and we're all done. With 63 though, we've got this weird situation where we're not normalized anymore. We've overflowed. We've changed the representation by rounding to the point that it's not normalized anymore. That's not going to fit into a floating point representation because we don't explicitly represent these bits that are to the left of the binary point. So I've got to do something about that. I've only got an implied leading 1 to work with. So what I'll do is just shift this whole thing to the right. And instead of having an exponent of 5, when I shift it to the right, that is in effect moving the binary point 1 to the left, right? If I shift the bits to the right, I'm implicitly shifting the binary point to the left, means I have to increase my exponent by 1. So I've got to adjust it. I've got to change it. So instead of 10.000 with an exponent of 5, I end up with 1.000 with an exponent of 6. And notice that these results are a little bit different. We've come as close as we can given the size of our representation, but notice that 128 stays 128, 15 stays 15, but because we had to do some of that rounding, 17 became 16. 19 became 20, 138 became 134, and 63 became 64. So this is a great illustration of how going from a real value, an actual value, the number that we started out with, and then expressing it in a way that a particular floating point format can handle might actually end up changing the value a bit. So to summarize what we saw in this video, we want to keep in mind that IEEE floating point has clear mathematical properties. Okay, we're representing numbers of the form m, some significand, times 2 to the e, some exponent. We can reason about operations independent of the implementation, right? We can assume we're going to compute with perfect precision and then round, right? So we can reason about these things and we can predict the outcomes, but we also want to keep very firmly in mind this is not the same as real abstract arithmetic. We're going to violate associativity. We're going to violate distributivity. And this is the kind of thing that makes life difficult for compilers, for serious numerical applications programmers, right? The more precision we need, the tougher things get when we're dealing with a computer system. And while floating point does a great job of expanding our options, it's still got those issues that we have to be aware of. And this is why we have to know exactly how things are working down at the level of the bits so that we know where we might run into trouble. So when you walk away from this video, you should be able to talk about how we go about implementing floating point addition and multiplication with an eye toward those problems we looked at. Because when we talk abstract math, there are certain properties that apply that simply don't apply when we're talking about floating point. And we should be able to implement floating point encoding, so normalization, rounding, etc.